Good morning, folks. Titmus here. Today, we're going to do the old bird on a wire problem. So, stretch your wings, grumble your gizzards, and preen your feathers, because here we go. Let's consider a 10-pound bird perched on a telephone wire. When she does this, the wire sags and makes an angle of 3 degrees with the horizontal. What is the tension in each side of the wire? That is, how much force does each wire pull with to support the weight of the bird? So, we start with a diagram. Then we list our knowns. Now, the 10 pounds refers to the bird's weight, or the force of gravity on the bird, which is mg. Now, we could rearrange this to find the mass of the bird if we wanted, but it isn't important for this problem. We could also convert to newtons, which would be necessary if we wanted the force to play well with meters or with kilograms, but none of that comes up in this problem, so we can just keep the force in pounds. Now, both theta 1 and theta 2 are 3 degrees, so we can just call them both theta. There's no need to distinguish between them if they're exactly the same. Then we want to find Ft1 and Ft2. Those are the forces of tension. Now, our first step with any problem that involves forces is to draw a free body diagram. This is drawn separately from our first diagram. All of the forces that act on an object are drawn starting on a dot that represents the object, and they all point away from that dot. It can be helpful to use dashed lines to represent the axes, and we should label the diagram as a free body diagram, or FBD. It is important that your force vectors are somewhat to scale. They don't have to be perfect, but if one force is larger than another, it should be drawn longer, or if two forces are equal, they should be drawn the same length. Sometimes you won't know this going into a problem. You won't know which one should be longer. So it's okay if the diagram isn't perfectly accurate. It is absolutely essential, however, that you label your forces with the kind of force it is, whether that's gravity or tension or friction or normal force, whatever it is. Here we have Ft1, Ft2, and Fg. Now, once we have a free body diagram, we can start to solve. We start by justifying our solution, by stating that the system is static, that is, it's not moving, and therefore there's no acceleration, and therefore all of the forces are balanced, which we will write in an equation form as sigma F equals 0, or the sum of all of the forces equals 0, right? If we add all of the forces together, they all cancel out. Now, just as we did with projectiles, we're going to split this problem into x and y axes because we have forces in multiple directions. This manifests as the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. Let's set up the x-axis first. The forces in the x-axis are Ft2x in the positive x direction, and Ft1x in the negative x direction, so it gets a negative sign on it. Those add to 0. This is just saying that the x components of Ft1 and Ft2 are equal and opposite, or that Ft2x equals Ft1x. Now, we can rewrite Ft1x and Ft2x in terms of the absolute forces Ft1 and Ft2 by using vector trigonometry. You may find it useful to draw out the vector diagrams, but it isn't necessary if you're very confident. But what we get is that Ft1x equals Ft1 cosine theta, and Ft2x equals Ft2 cosine theta. We'll come back for the y components in a bit. Now, if we substitute those into the equilibrium equation in the x-axis, we see that Ft2 cosine theta equals Ft1 cosine theta. And since theta is the same on both sides, the cosine thetas cancel, and we get that Ft2 equals Ft1. And we may as well dispense with the subscripts at this point, since they're all equal, and we can just call it Ft. It's worth noting at this point that this is only generally true if theta 1 equals theta 2. In the general case, these angles can be different, and tension 1 will not necessarily equal tension 2. But we're going to use the fact that tension 1 equals tension 2 in this specific case to make our math a little bit easier when we head over, right now, to the y-axis. Now, in the y-axis, the forces are the y component of tension 1 upwards, and the y component of tension 2 upwards, and the force of gravity, or the weight, downwards. So that gets a negative sign. And when we add all that together, it's equal to 0. Now if we rearrange this, we see that it simply means that the y components of tension 1 and 2 combined are equal and opposite to the bird's weight. Now we can return to our vector diagrams to see that ft2y equals ft2 sine theta, and ft1y equals ft1 sine theta. We know from the x-axis analysis that ft1 equals ft2, and we're just calling that ft. So we can make that substitution, substituting in ft, where we see ft1 and ft2 in the y-axis equation. And then we can combine our like terms. Solving for ft, we get mg over 2 sine theta. And now we can plug in our values. When we do that, the weight is 10 pounds, and the angle is 3 degrees, and we get 95.5 pounds. If we round that to one significant figure, that's 100 pounds of force in each of the wires. Each wire applies almost 10 times the weight of the bird to the telephone pole. This is crazy. So what we can see from this is that clever arrangements of wires or ropes can produce large increases of applied forces. So think about this the next time your car is stuck in the mud. This sort of thing also comes up a lot when people are rock climbing, and the rope might zigzag back and forth, and you have to think about the angles in the rope and how that might multiply the forces. So this crops up all over the place. Keep an eye out when you're out in the world for forces and tensions pulling in different directions. All right, guys, have a great day.